So what we're going to take a quick look at is stopping potential and the specific case of photoemission. The general case, what is stopping potential? Well, it's the voltage. Here's the voltage, by which I mean a potential difference. Needed to stop a charged particle. Okay, so you've got a charged particle moving along, it's the voltage you need to actually stop that charged particle moving. Now, before we look at this, we're just going to look at a general case of what goes on when things are speeding up and slowing down. Or slowing down. We'll just look at one of them, I think. So you've got speeding up and slowing down. Now, the one you're familiar with all the way from GCSE is a good old-fashioned. You've got some form of ramp and you've got a ball on top of the ramp. Initially, the ball's stationary, and as it goes down the ramp, funnily enough, it accelerates. You've got a height h here, and what you know in this scenario is that the kinetic energy gained is equal to the gravitational potential that's actually lost. So the gravitational potential energy lost. So you'd quite happily put in, well, half mv squared must be equal to mgh, assuming it started off as stationary. Now, the same thing goes on with charged particles, the whole same idea. So if you can imagine what I've got is I've got something that a plate at 0 volts, and I'm going to say that plate goes to another plate at plus 3 volts, and so I'm going to have a little electron. So a little electron, and that electron is going to move between those two plates. So in this case, it's exactly the same idea, but your kinetic energy gained is going to be equal to the electrical potential lost. So a half mv squared is going to be equal to, well, in this case is going to be equal to QV, but in this case I've got an electron, so it's actually going to be EV, or E times 3 volts, or 3E, in terms of the energy actually, electrical potential lost, which must be equal to kinetic energy. Now, if you can imagine, we've got the other way. If I fired something off and try to get it up a hill, I would be losing kinetic energy, gaining gravitational, till the point where I stop. And equally in this scenario, if here, say I used a proton and fired it from the 0 volt plate towards there, it would be repelled. So it'd be slowing down, losing kinetic energy, gaining electrical potential energy. So we've got this model, and that's basically all we're going to be talking about in terms of stopping potential. So let's look specifically at the photoelectric effect. Now, if we look at the photoelectric effect, and what we're going to do is we're going to put it in a circuit so we can investigate it just a little bit more. So what I'm going to have then is a basic circuit that goes around. I need to measure the current, so I'll have a microammeter, I'll have a power supply, I will take that back around over here. Let's make this a photoemitter. So a photoelectron emitter. And we're going to be shining light onto it. And what's then going to happen is this is going to emit an electron, and that electron is going to move to that point there. That point we're going to call an electrode. Okay, so typically what happens in this circuit is light shines on here. Forget the power supply set on 0 volts. The light shines on here. What will actually happen then is the photoelectrons will be emitted. Some will reach the electrode, and if they reach the electrode, you go all the way around in terms of a current. Now you can make it harder or easier to reach this electrode. It's a negative electrode. Electron. If I make this electrode here positive, it's going to be easier for electrons to get across. They're going to gain energy as they move between the two and speed up. Equally, if I make this electrode negative, what's going to happen is the electron's going to be repelled by that, so it's going to slow down. So if you can imagine, if that's positive, electrons are gaining energy, speeding up. That's negative. The electrons as they move across will be losing kinetic energy. Now you can imagine that some of them might not have enough kinetic energy to get across. And at that point, we call it they've been stopped. So first off, let's just remember a few things. So the photoelectrons are emitted with a max kinetic energy, which I'm just going to call the Ke max. And we should remember, hopefully, that the Ke max is equal to HF minus the work function. So it's equal to the energy supplied less the work function, which is the energy to actually get it off that surface. Next one we've got then, so stopping potential. Is the lowest voltage at which no electrons reach the electrode. So what I'll do is I'll just put a voltmeter across here so I can measure it. And you can imagine that if I've got a positive voltage between here and here, or if I've got this side positive, it's going to be attracted. Actually, I'm going to draw that out just to make this 100% clear. So there's my electrode. There's my photo-emitting surface. And if this ends at 0 volts, if this is at minus 3 volts, it's going to be attracted. Sorry, it's going to be repelled. So it's going to slow down. So an electron is going to slow down. And if it was positive 3 volts here, it would be attracted. Because the negative electron will be attracted to the positive there. All right. So what's actually going on in terms of this setup? So the first thing we know is when an electron moves between here and here, we know how much energy there is. Well, let's just consider each scenario is probably going to be easiest. So I've got a certain amount of kinetic energy that is going to be emitted by these electrons. And when they go here, they're going to have a change in potential. So the change in potential then, so the change in electrical potential is going to be QV, but we're talking about one electron, so that's just EV. So here I'd be gaining or losing potential energy based upon that. And it's a good old E equals QV equation from GCSE. So there are various scenarios here. If my kinetic energy, so my maximum kinetic energy of this, is greater than the EV lost, so is greater than the energy lost. So if you can imagine what happens here, so I should say here, I'm considering this scenario where it's got a negative voltage over here, and the energy here then is going to be QV. So if the kinetic energy is greater than EV, then my particles have got enough energy to reach the other side. What will happen then is you'll get a current registered around this. So you would see a current. The second scenario then is if my kinetic energy is equal to my potential that I'm going to gain as I go across because I'm repelled. So in that case, what would happen is be this magical scenario where the electrons actually stopped. Literally at the plate. The third scenario then is my kinetic energy I've got is less than the gain in electrical potential energy as you go across, and at that point there will be no current. Now actually, if you think about it as well, if the electrons are stopped, they don't make it around the circuit, so here there's no current as well. And we actually call this the stopping voltage or stopping potential. It's the smallest voltage at which point the current stops flowing, because then the electrons have got enough kinetic energy to get between here and here. Right, so that's our voltage. And you can set this up in a practical. And you literally run this and you increase the voltage on the power supply till in the end your current goes down to 0. And at that point, that is your stopping potential, your stopping voltage. Now, why would we ever bother doing this? Well, one scenario is if we wanted to find the work function. Now, if you could imagine, somehow we have to figure out what the work function is of a material. And let's make sure we've still got this here. So I'm just draw a brief diagram of circuits. Actually, you can still see the circuit up there, so it's fine. What we're going to consider then is the kinetic energy of the electrons is equal to E stopping voltage, we've said over here. And we know that for photoelectric effect, the kinetic energy max is the energy supplied by the photon minus the work function. Now, that means E stopping voltage must be equal to HF minus the work function. So, if we set up this circuit, we can know the frequency of the light we put in, relatively straightforwardly. We can measure the stopping voltage, relatively straightforwardly. So, if we know the stopping voltage, we obviously know the charge on the electron, we know the frequency of the light, we know Planck's constant. If I just rearrange this, I can then, by using this experiment, find E equals HF is equal to minus EVS, actually what the work function is. By measuring or knowing the frequency of the incident light source, by knowing the voltage actually across here, at which point the current stopped. Hopefully that makes sense. Thank you very much.